Hello, a very good morning to all, and welcome to my class. Today, we are going to start our new chapter, that is the transition elements and coordination compounds. So, basically, in today's class, we are going to cover the transition element, and in the next class, that is tomorrow, we are going to cover coordination compound as well as some PYQ questions related to the these two chapters only, right? So, let's start with the today's session, that is the transition elements. I hope my voice is audible to you and my screen is also visible to all of you, right? If you face any problem related to this, you can text me so that we can sort out this problem, right? So let's start with the today's session. What do you mean by this term D and F block elements, right? So in starting, we're going to cover some important and basic, fundamental things, and later we are going to discuss all the properties of D and F block elements, right? So first, in first half, we are going to understand the concept of the D block elements, and later half, we are going to understand F block element in detail, right? So what is this D block element? So basically, these are the element having completely filled outermost shell and incompletely filled inner shell. So this is very important to understand. D and F block elements are like these elements having a completely filled outermost shell. So they have a completely filled outermost shell like for NH2, right? And incomplete filled inner shell. So their inner shell is incompleted, right? If last electron enter into the penultimate shell, what is penultimate shell, beta? Basically, the inner shell, that is a one which is an outermost shell is known as outermost shell, and the just one cell behind outermost cell is known as a penultimate cell, right? So if the last electron enter into the penultimate shell, that is n minus 1 d orbital, then elements are called d block elements, where when it enter into n minus 2 f orbital, then the element are called f block elements. So we can easily remember what is d block elements and what is f block element, right? So basically, if the last electron enter into the penultimate cell, that is n minus 1 d orbital, if n minus 20 orbital means what? If the outermost cell, like let us assume it is a 5s, right? 5s. So 5s2. So penultimate cell be like 4, right? So 41, 42, 43. It may be anything between 41 to 1 to 10, right? So if the last electron enter into the penultimate cell then of the d orbital, then the element are called d block element. And if it's enter into n minus 1 f n minus 2 f orbital, then the element are called f block element. So these are the general definition of d blocks element and f block element, right? Now, classification of the d block element, that how should we classify the d block elements? So basically, these elements make up a three complete rows of the 10 elements, right? So these elements make up the three complete rows. So in a 3D series, 4D series, and the 5D series, so total we have a three complete rows of the 10 elements and an incomplete fourth row in the periodic table. So basically, D block element consists of a three complete row and each having 10 elements in it, like 30 elements. And the fourth row is an incomplete fourth row in the periodic table. These rows are named as 3D, 4D, 5D, and the incomplete were also named as 6D series, respectively. So this is the classification of D block. Now, as we can see in the different series of D block elements like 3D series. So in 3D series, they lie under the group of third B, similar the titanium lie under the group of 40. So how will you remember the 3D series beta? So 3D series we can remember like a scandium to zinc. That is science teacher, very cruel, mange fair copy. That is nickel copper zinc. So this is the trick, so that how we should learn this element of the 3D series. Basically, 3D series elements are very important. Many questions will come directly from this series only, right? So these 3D series are very important to understand, okay, so that you can know solve questions in a easy way. So just remember the name of the element, that is scandium to zinc. Scandium is the starting element whose atomic number is 21, and zinc is the last element of the 3D series whose atomic number is 30. Similar, last electron of the last element of the 4D series is cadmium, and the last element of the 5D series is nothing but mercury. So just remember these three, that is the zinc, cadmium, and mercury, because they show exceptionally different behavior as compared to rest of all the other element, right? They show exceptional behavior, exceptional exceptional properties. So they show exceptional properties as compared to rest of all other element of the D block elements, right? Because they have a fully filled electronic configuration, so they do not have any unpaired electrons. That's why they are not also colored. They are a colorless compound. So these are some properties shown by these three elements, that is zinc, cadmium, and mercury. So remember this, zinc is the last element of the 3D series, and the cadmium is the last element of the 4D series, and mercury is the last element of the 5D series having atomic number 80. Right. So this is how will you remember. So just remember these three and these three as well. Right. These three element as well. These three play also very, very important role. That is the second last element of the 3D series is copper. Similar 4D series is silver, and the 5D series is gold, right? So these three elements. So just remember this element like this, like last element of each row, like each period, right? Like 3D series, 4D series, and 5D series, and similar the last electron of the second last electron of the 3D, 4D, and 5D series. That is copper, Au, and Ag. So this one is very, very important. Understand? Good. So this will really help you if you know this atomic number in their position. It will help you in solving their question. Right. Now, what next? So basically the general and the physical property that we are going to study here is that is the electronic configuration. Right. So first of all, we need to understand that is the electronic configuration. So what electronic configuration they show? So basically the general electronic configuration of this metal is n minus 1 d 1 to 10 nh2. Right. So this is known as a penultimate cell. Right. This is known as a penultimate cell. Penultimate cell. Okay, and this is known as outermost shell. So this is known as outermost shell. Okay, so one is known as penultimate cell, another is known as outermost cell. So these are the electronic configuration. So general electronic configuration of this metal is like this: n minus 1 d 1 to 10 ns1 2. Right. Here it is obvious that the electronic configuration of this element differ only in the number of electron in their penultimate cell, that is d orbital, right? Because in ns they having either electron 1 or 2, so they are already same, either it will be 1 or 2. But here it obviously the electronic configuration of the element differ only in the number of electron in their penultimate shell, that is the d orbital. Thus they do not show a regular trend of the physical and chemical properties like s and p block elements, like, so they do not show a regular trend in the trend of a physical and chemical properties like S and P block elements, right? So they show some irregularity as compared to S and P block elements. So I hope this is clear to you. What is the general electronic configuration of the D block element? This is nothing but N minus 1, D1 to 10, NS1 to 2, right? And they are different only in the case of penultimate cell, that is in a D orbital. They do not show a regular trend of the physical and the chemical properties like S and P block element, right? So these are the electronic configuration of. I hope this is clear to you. Good. Now, half and completely filled sets of orbital are relatively more stable, right? So half and completely filled sets of orbital are relatively more stable, like chromium. So chromium we know that what is the atomic number of chromium in general? So in general, we write the electronic configuration of chromium as 3d4 and 4s2, right? Since we know that D having 5 orbitals, out of which 10 electrons are placed. So they are either fully filled having 10 electrons or half filled, which having a 5 electrons. So chromium are stable either in half filled or fully filled. So for it, say fully filled is not possible to attain 10 electrons. So it acquire half filled electronic configuration. How? They will accept 1 electron from 4s2, so they will become 3d5, and this will become 4s1. Now this is much more stable, right? This is much more stable because they having electronic configuration of half filled, right? So half filled and completely filled sets of orbital are relatively more stable, like chromium having electronic configuration 3d5 and 4s1. Similar, copper having atomic number 29, we know that the electronic configuration nothing but that is 3d9, and this is 4s2. They also want stability. So do so, it will take 1 electron from S, so it will become 3d10 and 4s1, right? So these two show that half filled and completely filled sets of orbital are relatively more stable, and every element which is nearer to this electronic configuration has a higher probability, higher chance, higher, higher capability to get this electronic configuration like half filled and full filled, right? So these are the electronic configuration. Okay. Now the electronic configuration of zinc, cadmium, and mercury that we already discussed are represented by the formula that is n minus 1 d ns12, right? So how will you represent? Because they have a fully filled electronic configuration, right? So they are nothing but they have a fully filled electronic configuration. Like if I'm talking about zinc, so they have a electronic configuration like 3d10 and this is 4s2, right? Similar if I'm talking about the cadmium, right? Cadmium, they have a again 4d10 and this is 5s2. Similar if I'm talking about the mercury, their electronic configuration 5d10 and this will be 6s2, right? So these all have a 10 electron in their outermost electron and they are no, they are completely fully filled and stable. Due to this, they do not show any unpaired number of electron, and due to this they are colorless in aqueous and they are not called transition elements. So they have a fully filled electronic configuration. So they have fully filled they have fully filled electronic configuration, right? So they have a fully filled electronic configuration. Okay, so they have a fully filled electronic configuration, and due to this, they are called non-transition element. They are called non-transition element, right? They are called non-transition element because they do not possess any unpaired number of electrons. Okay, so that's why they are called non-transition elements. I hope this is clear to you all. What is half filled and completely filled, and why zinc, cadmium, and mercury are not regarded as transition element because they have a fully filled electronic configuration. They do not have any unpaired electron. So if they do not have any unpaired electron, then they were not called as a transition element because we call transition element when they have a something some amount of lone pair, or we say one or two lone pair of one or two unpaired number of electrons. If they do not have any unpaired electrons, then we cannot say it is a transition element. I hope this is clear to you. Good. Now, atomic radii. So this play also very like S block and P block, we not get any regular trend like down the group atomic radii increases, left to right atomic radii decreases. So this type of trend we cannot get in the D block element because they show irregularity in their behavior. So in a given series, the atomic radii of these elements generally decrease from group 3 to group 10. So you must remember this in a given series the atomic radii of these elements generally decrease from group 30 into group 10 and after that increase again toward the end of the series. So toward the end of the series, quickly show me the periodic table so that you will understand. Now, till group 10, right? I'm talking about from group 3, right? Group 3 and here we have a group 10. So from group 3 to group 10, there is a decrease in the size as we move from group 3 to group 10, but there is suddenly increase in the group 11 and 12, right? So there is suddenly increase in group 11 and 12. So why this is happening? Why the size is decreases from group 3 to group 10 beta? So this is because the nuclear charge increases with the increase in the atomic number. So this is a very simple concept. We already know whenever we move from left to right in the periodic table, the size decreases. And the reason behind this is nothing but this is the increase in the nuclear charge with the increase in the atomic number. Now, due to this, the electron clouds are attracted more strongly. So what is happening now? Due to this nuclear charge, the electron clouds are attracted more strongly and result in the decrease in size. However, the decrease in the radii across the period is not uniform, right? So, however, decrease in the radii across the period is not uniform. That is the radii of the element from chromium to copper are very close to one another, right? So we are talking about if the radius of the element from chromium to copper are very close to one another, because if you're considering the fundamental rule, like when you move from across the period, the size decreases. But here the radii across the period is not uniform, right? Because the radius of element of chromium and copper are very close to one another. Why this is happening? So this is due to basically the effective screening of outer NS electron by the electron into N minus D subshell. And the reason from this anomalous increase in the atomic radii towards the end of the series is due to the predominant repulsion between the added electron. Let me explain what is happening. What is happening, right? Because let's see, this is the nucleus. This is the number of shell of electrons, right? So as we move from left to right, number of electrons increases, and these electrons are added into the penultimate shell, that is 3D. Now, these having two electrons, N is two electrons. So these having NH2 electrons, and these having D electrons. So if example, if only two electrons are there, now this will become 3, now this will become 4, this will become 5, this will become 6. So as the number of electrons are increasing, they provide repulsion to their outermost electron, right? So these electrons provide repulsion to this outermost electron, because as the number of electrons start increasing, repulsion dominated, right? So the reason for the anomalous increase in the atomic radii towards the end of the series due to the predominant repulsion between the added electrons. So when we added electrons are there, they predominate repulsion is taking place. So this is called the effective screening of the outer NS electron by the electron of N-1 d subshell. So the electron present in the penultimate shell, that is N-1 d subshell, as the number of electrons start increasing, they providing screening to the outer NS electron. Screening means they repel this electron, and due to this the attraction between the outermost electron and the nucleus decreases. As a result of this, what happening now, size is suddenly start increasing, right? So this is the reason, because of the predominant repulsion between the added electron. Now, presence of completely filled d orbital also decrease the force of attraction. Now, on moving downwards in the group, the atomic radii increase. All through, the increase is not significant as in case of SN flip. As we observe an S&P block, there is a very significant amount of increase in the size when you're moving down the group due to increase in the number of shells. But in case of PD block elements, on moving down the group, the atomic radii increases. All through, the increase is not as significant as in case of SN-P block elements. So this point you must remember, right? Now, the member of 4D and 5D series exhibit near about similar radii, which is due to the lanthanoid contraction, right? So the member of 4D and 5D series exhibit almost about the similar radii. Now, what happening in the S block, P block, we know that while we moving down the group, the size increases, but this is not happening in the D block. The size of 4D and 5D, their size is almost remain same. Okay, so the member of the 4D and 5D series exhibit near about similar radii, which is due to the lanthanide contraction. What is lanthanide contraction? That is the filling of 4f electron before 5D result in decrease of the atomic size, is an increase in the atomic number. So this is known as lanthanide contraction. We are going to study in the F block element as well, right? So basically, the member of 4D and 5D series exhibit near about similar radii, which is due to the lanthanide contraction. So this is how we represent the size of the atomic radii of the transition element, right? So this circle represents basically the first 3D series. So this represents the 3D series. This represents 4D series, and this represents 5D series, right? So this is the 3D, 4D, and 5D series. So this graph is between the radius and the plot of radii with the atomic number. So in this, we have an atomic number, and this is we have a radius. So now, if I'm talking about the scandium, as we can see that the size of a scandium is much more. Then there is a decrease in the size from titanium. Then there is also decrease, 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 decrease. Now, we can observe that the size of Fe, Co, and Ni, they are almost same, right? Their size are almost same, and they are suddenly increase in the size again. So in from starting, that is from scandium to titanium, vanadium, chromium, and manganese, there is a decrease in the size, right? However, the size become constant when you move from manganese to copper. Why? Because here the attraction is equal to repulsion, right? So here the shielding effect is balanced by this. So we can say that we get the opposite and equal and opposite forces. But what happening in the zinc, that due to the increase in the shielding effect, more shielding effect due to the addition of added electrons, their size start being increasing, right? So their size start being increasing. Same happening for the 4D, and for if I'm talking about the 4D, that is the size of Ru to Ag, they almost remain same. And we can also observe that that is a 5D. So the 3D and 5D, there is a very less size difference between the 4D and 5D curve, where in case of a 3D curve, we get the significant amount of size difference between 3D, 4D and 5D. But the 4D and 5D are almost remain same due to the lanthanide contraction comes into the picture. If we're talking about the 4D and FD orbitals. I hope this is clear to you. 4D and 5D subshell, sorry. So I hope this is clear to how atomic radius, how atomic size varies in the transition element. Right. Now, hence we can say that zirconium and HF, Nb and Ta, right? Where is zirconium and HF? So this is nothing but zirconium and HF, right? This is zirconium and HF, Nb and Ta, right? Tungsten and mobillion, right? So tungsten and mobillion, T and Re are called chemical twins. So they are called chemical twins. Why they are called chemical twins, beta? Why they are called chemical twins? Because their atomic size are almost same as compared to each other. So ZR and HF have a very similar properties and chemical properties because of their smaller radius. ZR having the zirconium and atomic radius 160 picometer, where HF having the atomic radius 159 picometer, which makes their separation very difficult. And due to this, the separation of the transition element lanthanide series is very, very difficult. So this point you must remember, beta. If someone say is the separation of the transition element is easy. So you can say that no, the separation is not easy. Separation is very difficult because their size is almost same. If we're talking about zirconium and HF, then their size is almost same. So this is all about the atomic radius. So I hope it is clear to you what is atomic radius all about. Now, let's see the ionic radius. So the ionic radii of this element follow the same trend as they are the atomic radii. In case of ions carrying identical charges, the ionic radius decrease slowly with increase in the atomic number in the series. The ionic radii decrease with the increase in the oxidation state as well. For the same oxidation state, ionic radii generally decrease with the increase in the nuclear charge, or we say that is increase in the atomic number, right? So next is the molar volume density. So what is this molar volume and density? So basically the molar volume of d block elements are much lower than those of s block elements of a neighboring group. Why? It is because reason that as the inner orbital gets filled, the increased nuclear charge pulls the electrons inward. Right. So what is happening basically? So as the inner orbital gets filled, at the inner orbital, that is 3D orbital get filled, 3D1, 3D2, 3D3, 3D4, 3D5. So as it goes on, the increased nuclear charge pulls the electron inward. So this nuclear charge pulls the electron inward. Due to such decrease in the molar volume, as increase in density is seen. So we know that density is equal to mass upon molar volume. So if so if there is a due to such decrease in the molar volume and increase in the density is seen. In a series from left to right, density increases because we know that volume decreases as we move from left to right. So on moving down the group, density increases, right? So just remember this thing on in a series from left to right, density increases, and on moving down a group, density increases. So this will you must remember, right? Now, the most important thing is ionization energy. So what do you mean by this term? Ionization energy. Okay. Now, since the atoms are smaller in size, their ionization energy is fairly high, right? And the value in most cases lie between p and s block elements, right? Thus indicating that transition metal are less electropositive than the element of s block element, right? And less electronegative than the p block element, right? So their atoms are smaller in size and their ionization enthalpy are fairly high, right? So their ionization enthalpy are fairly high. Now, The value in most cases lie between those of p and s block element, thus indicating that transition metal are the less electropositive than the element of s block elements, right? Now, we can observe the ionization enthalpy through this following graph, right? So in the y-axis, we are taking ionization energy. In the x-axis, we are taking element, name of the element, right? So if I'm talking about the first ionization enthalpy, right, first ionization enthalpy of the scandium, second and third. So we can observe that the first ionization enthalpy of the scandium is around between anything 0 to 1000, that is around 700. And the second one is between this and third one between this. So we can observe that the consecutive ionization enthalpy start increasing when you when you have to calculate for IE1, IE2, and IE3, right? So basically, what is IE1? Basically, scandium is nothing but it is equal to 3D1 and this is 4s2, right? So in first case, we have to remove the electron from this one and from again one and for 3D2, right? Okay. Similar in case of titanium. Here we can observe one important note here. That is the second ionization enthalpy of Mn and Fe are almost same, right? Where the third ionization enthalpy of Fe are lower than that of Mn. How will you explain this? Let's see. If I'm talking about Mn and I'm talking about Fe. So Mn having electronic configuration 3d5 and 4s2. Similar Fe having electronic configuration 3d6, 4s2. So let's talk about their first ionization enthalpy. So I'm talking about the first ionization enthalpy, then their value is like one electron is removed. If I'm talking about the second ionization enthalpy, then two electron will be removed into 4s2. Now, if I'm talking about the third, then we have to remove electron and this will become 3d5. Stable, right? So they become stable. Similar in case of Mn, if the two electrons are released, emitted, then it will become 3d5. So for Mn plus 3, for removal of plus 3, you have to remove electron from the stable, right? From the stable electronic configuration. So obvious the amount, the high amount of ionization energy you require to remove the electron which is already in the stable form. So it is required high amount of energy. So we can observe that the third ionization enthalpy of Mn3, right? The third ionization enthalpy of Mn3 is slightly more as compared to the third ionization enthalpy of Fe, right? So this is the exception we get. Similar in case of chromium and manganese, the third ionization enthalpy of chromium is more as compared to manganese. So this is what we get. I hope this is clear to you. Okay, good. So this is how we understand the ionization enthalpy. In a series, the ionization enthalpy increases from left to right, but the increase is not so pronounced as in case of S and P block element, right? So basically, in a series, if I'm talking about the series, the ionization energy increases when you move from left to right, but the increase is not pronounced. That is in case of S and P block element, because in S and P block element, the increase is very significant. We can clearly observe. But in the 5D series element, it is higher than the element of the 4D and 3D series, right? So we can understand this thing. The ionization enthalpy of 5D series element is higher than that of 4D and 3D. Why? So this is due to the greater effective nuclear charge acting on the outer valence electron because of the weak shielding of the nucleus by the 4f electron. We know that the shielding order is like best shielding is shown by S, then P, then D and F. So D and F, they show poor filtering effect, right? So D and F show poor filtering effect, and due to this only, 5D series element is higher than the element of the 4D and 3D series ionization energy. Now, IE2 of the first transition series increase almost regularly with the increase in the atomic number. As we can see that the IE2 of the first transition element increase with the increase in the regularly with increase in the atomic number. However, the value of chromium and copper are sufficiently higher than those of their neighboring, like chromium and copper, right? So chromium and copper having values slightly greater than those of the neighboring atom, right? Now, this is due to the stable electronic configuration and the ionization energy of zinc, cadmium, mercury are abnormally higher due to their completely failed orbital. Now, this is the some data, then how we'll actually confirm the ionization energy of the d block elements. So this is the 3D series element having ionization enthalpy like this, that is 631, 656, and like this. Okay. 650, 653, and so on. Similar, if I'm talking about the 4D elements, they having ionization enthalpy like 416, this, and La having the ionization enthalpy of 551, HF having the 761. Because in La and HF, we have a 14th electron we have of a block element, right? That's why their small size becomes so small. Ionization enthalpy will increase. So this is the data that we get. That is element of the 3D series, element of the 4D series, element of the 5D series, and their ionization energy. Now, the sum of the first three ionization energy for scandium is little less than than the sum for the aluminum, right? So the first three ionization energy for scandium is little less than the sum of our aluminum. Thus, the property of scandium are similar in some ways to those of aluminum. The magnitude of ionization energy give an idea about the relative stability of the various oxidation state of the transition element. So this ionization enthalpy gives us the idea how relative stabilize of the various oxidation state of the transition element, right? So this is what happening. Thus, the properties of scandium are similar in some ways to those of aluminum because the sum of the first three ionization enthalpy for scandium is a little less than that sum for the aluminum. Now, example, nickel 2 compounds are thermodynamically more stable than platinum 2, while platinum 4 compounds are relatively more stable than nickel 4 compounds. So why this is happening? It is because of the sum of their ionization enthalpy. If I'm talking about the nickel and platinum, their sum of the ionization enthalpy 1 and 2 is like this. Right. If I'm talking about the nickel having electronic configuration, science teacher very cruel mange fair copy nickel, that is 3D8. So this will become 3D8 and 4H2. So ionization enthalpy 1 and 2. This will become 3D8 on removing the 2 electron. Right. So this will become an nickel 3D plus platinum is also. So basically they are more stable than nickel compounds. So nickel compound are thermodynamic much more stable than platinum 2. While platinum 4 compounds are relatively more stable than nickel 2, it is basically due to the value of the ionization energy. So those having the higher ionization enthalpy values are much more stable as compared to those having the less amount of ionization enthalpy. Now, the next is nature of bond, right? So unlike alkali and alkaline earth metal, the transition element have tendency to form covalent bond along with the ionic bond, right? So this point is very, very important. Understand this thing. Unlike alkali and alkaline earth metal, the transition element have a tendency to form covalent bond along with the ionic bond. So they have a capability of form both the bond, that is covalent as well as ionic bond. Generally, the compound in which the smaller vacancy is exercised are ionic, while those in which the higher vacancy from the covalent compound. So generally, the compound in which the smaller vacancy is exercised are ionic, while those in which the higher vacancy from the covalent compound. Right. So this is all about the nature of bond they form. Now, what is metallic character of the D block element, right? So let's see the metallic character of the D block element. So all the transition elements show typical metallic properties such as the high tensile strength, ductility, malleability, high thermal and electrical conductivity, metallic luxure, except zinc, which is liquid at room temperature. So remember this, all transition elements show typical metallic properties. So all the transition elements show typical metallic properties such as high tensile strength, ductility, high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. So except zinc, which is a liquid at room temperature, all show these properties, right? So with the exception of zinc, cadmium, and mercury, all the transition elements are much harder and they're very less volatile. Exception of this zinc, cadmium, and mercury. Zinc, cadmium, mercury do not contain any unpaired number of electrons. Due to this, only they are colorless as well. Their salts are white in nature and they are very soft. They have a less bond dissociation energy as well. So chromium, molybdenum, and tungsten contain the maximum number of unpaired electrons, and as such, these are hardest metal in their respective period. So chromium, molybdenum, and the tungsten contain the maximum number of unpaired electrons, right? Now, all through the hardness and brittleness are associated with the covalent bond between the metal atom. The existence of metallic bond cannot be detailed, right? While the overlapping of unfilled d orbitals of metal cause covalent bonding, like Cu, Ag, Au are particularly outstanding in their thermal and electrical conductivity. So these all are the point related to the metallic character. So I hope this is clear to you all. Anyone having any kind of doubt, you can ask. ठीक है समझ आया सबको the next is the next is enthalpy of atomization ठीक है the atom of transition elements are closely packed, right? So the atom of transition element are closely packed. They are held together by a strong metallic bond, right? Just wait a minute. Okay, ठीक है. So the atom of transition elements are closely packed and they are held together by the strong metallic bond. Because of the presence of large number of unpaired electron in their atom, these possess high enthalpy of atomization. So remember this, they are held together. The first point is they are held together by the strong metallic bond. And because of the presence of large number of unpaired electron in the atoms, they possess high enthalpy of atomization. The metal of second, third series have a greater enthalpies of atomization than the corresponding element of the first series. Just remember this. The metal of second, third series have a greater enthalpies of atomization than the corresponding element of the first series. So this is all about the enthalpy of atomization. What point you need to be remember? First, the atom of the transition element are closely packed and they are held together by the strong metallic bond because of the presence of large number of unpaired electron in their atom and they possess high enthalpy of atomization. And next, the metal of second series and the third series, right, have a greater enthalpy of atomization than the corresponding element of the first series, right? Now, let's talk about the melting and the boiling point. So their melting and boiling points are high, which is attributed to a strong interatomic bonding involving participation of NS, Nn-1d electron that is metallic bonding is stronger in them. So they show good metallic bonding. Why they show high melting and boiling point? Due to presence of unpaired electron and they form a strong bond, right? So their melting and boiling points are high, which is attributed to a strong interatomic bonding involving participation of Ns and N-1 2 electrons, right? Now, in any row, the melting point of these metal rise to a maximum at D5, right? So in any row, the melting point of these metal rise to a maximum at D5 except for anomalous values of Mn and Tc and fall regularly as the atomic number increases. So remember this, in any row, the melting point of these metal rise to a maximum at D is equal to 5 except for anomalous values of Mn and Tc and fall regularly as the atomic number increases. Okay. However, zinc, cadmium, and mercury, due to presence of completely filled N-1d orbital, are not expected to have a covalent bonding. Thus, their melting and boiling point are relatively low as compared to the other element of this block. So, this exception you need to remember every time. That is the zinc, cadmium, and mercury. They show a different behavior as compared to rest of the all elements, right? So this is the case here. That is the zinc, cadmium, and mercury due to presence of completely filled N-1 d orbital are not expected to have a covalent bonding. Thus, their melting and boiling points are relatively low as compared to the other element of this block. So this is all about the melting and boiling point. So this is the graphical representation of the melting point so that you can understand this thing. So this is the melting point order of 3D, 4D, and 5D series element, and this is not according to the scale, this is according to the experimental data, right? So let's see. If I'm talking about the scandium, titanium, vanadium, and chromium, so still their melting point is increases. As we already discussed, in any row, the melting point of this metal rise to a maximum at D is equal to 5, except for the anomalous values of Mn and Tc, and fall regularly as the atomic number increases, right? So 3D1, 3D2, 3D3, 3D4, and 3D5. So 3D5, there is a decrease in the value, right? There is a decrease in the value. So rise to a maximum, and at D5, except for Mn and Tc, fall regularly. So here the values start decreasing. So from Mn, that is Fe, Co, and nickel. So these all show a very, very less melting point. Similar, if I'm talking about the second group, that is lanthanum, zirconium, Nv, and this is Mo, then start decreasing. Okay. Again, there is a huge increase in case of tungsten. So this is the melting point order, so that you can remember from this graph as well. Now, the next is oxidation state. So what do you mean by this term oxidation state? So basically transition elements show a large number of oxidation state differing usually by the unit of one, right? So they show a large number of oxidation state which are differ only in the oxidation number. Some say +3, some say +2. So they are different only by +1, right? So unit of one only. So transition elements show a large number of oxidation state. This is due to fact that N-1d electrons may get involved along with the Ns electron in bonding, as electron in N-1d orbital are in an energy state, right? Are in an energy state to a Ns electron. How we understand this thing? Why the transition element show a large number of oxidation state? This is because N-1d electron may get involved along with the Ns electron in the bonding. So here in bonding, not only Ns electron that will participate, but in bonding here also penultimate shell, that is N-1d orbital and Ns electron, both takes place in the bonding. Now, as electron in N-d orbital are in an energy state comparable to the Ns electron, the stability of the given oxidation state depends on the nature of the element with which the transition metal is combined, right? So the stability of the given oxidation state is totally depends on the nature of the element with which the transition metal is combined. The highest oxidation state are found in the compounds of fluoride, oxide, because of the most electronegative nature of oxygen and fluorine. So due to the most electronegative nature of fluorine and oxygen, we find the highest oxidation state in case of food, right? So I hope this is clear to you. Good. Now, oxidation states of first transition series. That is the oxidation state of the first transition series like scandium, titanium, vanadium, chromium, manganese, Fe, and this. So we can understand their oxidation state. For example, outer electronic configuration of scandium is nothing but 3d14s2. So the oxidation state either this 2 electron and plus 1. So this 3 electron takes place in participation of bond formation. So they show maximum oxidation state of plus 3 only. Now titanium show either plus 2, or will they show plus 3, or will they show plus 4. Similar vanadium show either plus 2, plus 3, plus 4, or plus 5. Similar chromium show plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. Manganese show till plus 7. Now again Fe starts showing either plus 2, right, or we say plus 3, or we say plus 4, or we say plus 5, or we say plus 6. So it will show maximum oxidation state up to 6. Similar 3d74 it will show either plus 2, plus 3, plus 4. 3d8 it will show either plus 2, plus 3, or we say plus 4. 3d10 it will show either plus 1 and plus 2, and 3d10 it will show either plus 2 only, right? So we can observe here a very important thing, and this important thing is maximum oxidation state shown by the element of the 3D series is what? Let me write, just wait for a minute. Okay, so manganese, right? Manganese, so maximum oxidation state till plus 7. So the maximum oxidation state in the 3D series is shown by the manganese, right? We show the oxidation state up to plus 7. Now, the oxidation state of element of second and third period series are like if I'm talking about the second transition element, like Y, zirconium, Nb, Mo, Tc, Ru, Rh, Pd, Ag, Cd. So Y show the oxidation state of plus 3, zirconium so plus 4, and so plus 3 plus 5, Mo say plus 3 plus 4 plus 5 plus 6. TC say show plus 4 plus 6 plus 7, and Ru is show up to the 8. So if someone asks what is the maximum oxidation state shown by the transition element, so you will show plus 8. What is the maximum oxidation state shown by the 3D series? So it will be plus 7. So this Ru show plus 8 oxidation state, which is maximum in the all transition element, right? Similar cadmium so only plus 2, Ag so plus 1 plus 2 plus 3. Similar oxidation state of the third transition element is like what? It is like plus 3 and plus 8 is also here. That is shown by the OS. So OS show oxidation state up to plus 8 on. Now, the first member of each transition series does not show variable valence, right? So the first member of each transition series does not show variable valency. Okay. It's generally show only plus 3 oxidation state. So the first member of each transition series, either it will be 3D, 4D, 5D, or maybe 6D. So the first member of each transition series does not show variable valency. It generally show only plus 3 oxidation state. Except scandium, the most common oxidation state of the first row transition element is plus 2, which arises due to the loss of 2 4s electron, right? So except scandium, the most common oxidation state of the first row transition element is plus 2, which arises due to the loss of 2 4s electron. Now, in second and third oxidation state, bond formed are mostly ionic. This point is also very important. In second and third oxidation state, the bond forms are mostly ionic. In the compound of the higher oxidation state, that is MnO4 negative, the bond formed are essentially covalent, right? So in the compound of the higher oxidation state, MnO4 negative, the bond formed are essentially covalent. Some transition metal also show oxidation of 0 in their compound, like NiCO4, FeCO5. So in such complexes, these transition element, that is nickel and Fe, they show a 0 oxidation state, right? In general, for the first 4 elements of the transition series, higher oxidation state are more stable than the lower oxidation state, right? Now, for the next 5 elements, lower oxidation state are more stable than the higher oxidation state. For example, chromium 3 is much more stable than chromium 2, right? But Mn plus 2 is much more stable than Mn plus 3. So this point is very important. So in generally, first 4 elements of the transition series, higher oxidation state are more stable than the lower oxidation state. And for the next 5 elements, that is the lower oxidation state are more stable, right? Now, among the group of the D block element, the higher oxidation state are favored by the heavier member. That is the opposite is true in the P block, right? So among the group D block element, the higher oxidation state are favored by the heavier element. That is basically the opposite is true in the P block. That is in group C, Mobilium 6 and tungsten 7 are found to be more stable than chromium 6. Now, the chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas MaO3 and OWE3 are not. Only Ru and OH show +8 oxidation state in their compound. Remember this. Now, what you need to remember from this? All copper 2 halides are known, whether you make copper bromide, copper chloride. So all copper 2 halides are known except iodide. Where? Because why iodide? Copper iodide is not possible in +2 oxidation state because copper 2 oxidize I negative to I2, right? Because copper 2 oxidize I negative to I2. However, many copper compound are unstable in aqueous solution and undergo disproportion, like 2 copper plus, it will undergo to give copper 2 plus and copper. So the stability of copper plus to aqueous rather than copper plus aqueous is due to much more negative delta H value of copper aqueous and then copper plus, which is more than that of compensate from the second ionization enthalpy of the copper, right? So whenever while solving problem based on the oxidation state, always keep in mind what point you need to keep in your mind. The first one is atomic number of the element and their electronic configuration. Right. So these are the very important thing while solving problem based on the oxidation state. Always keep in mind that the atomic number of the element and their electronic configuration. So this is the first requirement. The second, minimum oxidation state is generally +2, but it is +3 for the scandium and chromium and +1 for the Cu and Ag. Right. So the minimum oxidation state is generally 2, but it is the +3 for the scandium and chromium and +1 for the copper and Ag. Transition element is the lower oxidation state, that is +2 and +3 from ionic compound, while those in the higher oxidation state will they form a covalent compound. The maximum oxidation state for any transition element is found in its compound with fluorine and oxygen, as they have a very small size and they are most electronegative. Lower oxidation state found in a complex compound has a ligand like carbon monoxide, which is capable of pi acceptor character in addition to its sigma bonding. Right. So this is all about the oxidation state. So next property is standard electrode potential. So I hope till all the points are cleared. All points are clear till? Good. So let's study about the standard electrode potential. So what is this standard electrode potential? So basically the E0 values of all the transition metal except copper is lower, that is negative, than that of hydrogen, which is taken as 0. So we know in the case of electrochemical series, we already discussed this thing. The E0 value of all the transition metal except copper is lower, or we say negative, than that of hydrogen, which is taken as 0. Thus, all the transition element with the negative reduction potential liberate hydrogen from dilute acid, right? So the inert value of all the transition metal except copper is lower, or we say negative, only copper having the positive value. Then that of hydrogen, which is taken as 0. It means all lie above the hydrogen in the electrochemical series. Just one element, that is copper, which is lie below the hydrogen and having value 0.344. Okay. Thus, all the transition element with the negative reduction potential liberate hydrogen from the dilute acid. So this is the element, that is Em2 plus 2m in a volts. A voltage is given. This is minus 1.18, chromium 0.18. Copper, you have a value of plus 3.4 volt, right? Now, most transition metal are inert toward acid or react slowly with them because of the protective layer of the oxide, right? So the most transition metal are inert, right? So the most transition metals are inert towards acid or react slowly with them. Why? Because of the protective layer of oxide. In case of chromium, deposit a negative, despite a negative electrode potential, it is a quite inert chemically. Why? Because the formation of chromium oxide, Cr2O3, on its the surface. Similarly, Em2 plus M value are not regular for the 3D series element. The lower the electrode reduction potential, more negative the standardization potential of the electrode, right? Thus, more stable in the oxidation state of the transition metal in the aqueous solution. Okay. Now, the next point is, that is the reducing property. So before reducing property, just revise this till I take some water, and then we're going to start the reducing property. Okay, so what is the reducing property basically, beta? So all these elements of the 3D series except copper has a standard reduction potential lower than that of hydrogen, and hence all of them except copper are the good reducing agent, right? So we know from the electrochemical series. So those having the value greater than less than zero, because in electrochemical series we observe that hydrogen having the electrode potential value 0. So anything which is lying above, right, having negative electrode reduction potential value, and lying below are the positive standard reduction potential value. So all these elements of the 3D series except copper have a standard reduction potential value lower than that of hydrogen. Hence, all of them except copper are a good reducing agent. However, they are not as good reducing agent as the metal of the first, second, and 13th group, right? So, however, they are not as good reducing agent as the metals of the first, second, and the 13th, right? So, remember this. They are not as good reducing agent as the metal of the first, second, and the 13th group, like sodium, aluminum, magnesium. Now, colored compounds or complexes. So most of the compound of the transition metals are colored in solid state or solution. So most of the compounds of the transition metals are colored in the solid state or solutions. The color of a transition metals ion arises from the excitation of electron from d orbitals of lower energy to the d orbital of the higher energy. This is commonly known as DD transition, right? This is commonly known as DD transition. So the color of the transition metal ion arises from the excitation of electron from d orbital of lower energy to the d orbital of the higher energy, that is DD transition. The transition metal ion which have either completely filled d orbital or completely empty d orbital are colorless. Remember this point. The transition metal ion which have either completely filled d orbital, because in this all DD transition is not possible, or those having completely empty d orbital where there is no electron for the DD transition. So in such cases, the DD transition is not possible, and due to this, they are not capable of showing DD transition, and thus they are colorless, right? So the most of the compound of the transition metal are colored, and why? Due to the DD transition. For this, we need a repeat number of electrons. So transition metal ions which have either completely filled the orbital or completely empty the orbital are colorless because of there is no capable of showing DD transition. The color of a transition metal complexes is depend on how big the energy difference is between the two D levels, right? If I'm talking about the two D levels, we are going to study this thing in coordination compound as well. So let us assume this is the 2D orbital. This is called the D2G orbital. This is called the EG orbital. Right. So this is the d orbital dxy dyz dzx dx square y square dz square. So if the energy gap is more, right, this is energy gap is more. So the color of the transition metal complexes is depend on how big the energy difference between the two d orbitals. Depends on the nature of the ligand. So this splitting is depends upon the nature of the ligand. So if the ligand is strong, right, if the ligand is strong, then obviously this separation will be more, right? This separation will be more. So the type of the complex form, the color which we see in the color of the transmitted wavelength and its complementary color absorbed by the complexes. Now, in the series, scandium plus 3, titanium plus 2, vanadium plus 5, chromium plus 6, magnesium plus 7, all have an empty d orbital, hence DDA spectra are impossible. And such their compounds should be colorless. Like, because in scandium plus 3, we know scandium is nothing but 3d1 and 4 is 2. If you remove all these 3 electrons, it will become 3d0. So they have a no unpaired electron for the D transition. Similar, if I'm talking about the Mn plus 7. So in Mn, they having electron like 3d5 and 4s2. So if you have remove all these 7 electron, it will become 3d0. Right, it will become 3d0. So we can say that scandium, manganese, right? Scandium, manganese, chromium plus 6, vanadium, they all have an empty d orbital, hence DDA spectra DDA spectra are impossible and such their compounds should be colorless, right? But here important note, this note is very important. But VO2, that is here also, in case of VO2, that is 2 plus, right? Here also, vanadium is in plus 5 oxidation state. So plus 5 means what? That is vanadium normally, that is science teacher very cruel. That is 3d3 and 4 is 2. So in vanadium plus 5 oxidation, it is assumed to be 0 and it assumed to be no DD transition is possible. So it assumed to be colorless. But actually, VO2 twice plus is a colored compound. So how they are colored? So in iron in aqueous solution are colored. The color arises due to the charge transfer. Always remember this phenomenon due to charge transfer. So the color arises in VO2 plus, CrO4 twice negative, MnO4 negative. So in this all, the charge arises, okay? And this due to this, the color arise due to the charge transfer. So this is all about the color that we have already discussed in detail. Now, magnetic properties. So this will also play a very important role. So what is the magnetic properties? So basically, if I'm talking about the magnetic properties, so magnetic properties like many of the transition metal ion are paramagnetic. Why? Due to the presence of unpaired electron in them. So many of the transition metal ions are paramagnetic due to presence of unpaired electron in them. Each such unpaired electron have a magnetic moment associated with it. That is spin angular momentum, or we say and angular orbital angular momentum. So spin angular momentum and the orbital angular momentum. In transition element of compound, the orbital motion of unpaired electron is severally disturbed by the electron of the surrounding ligand. So basically, many of the transition metals are paramagnetic. Why? Due to presence of unpaired electrons in them. Each such unpaired electron have a magnetic moment associated with it, that is spin angular moment and the orbital angular moment. In transition element compound, the orbital motion of unpaired electron is severely distributed by the element of the surrounding ligand. Now, therefore, the contribution of the spin angular momentum become much more significant than the orbital angular momentum contribution. Hence, mu orbital contribution may be neglected, and we can find mu of spin is equal to under root n plus 2, where n is nothing but the number of unpaired of electron, and mu spin is the spin magnetic moment. Now, where n is the number of unpaired electron, magnetic moment directly proportional to the number of unshared electron. If the number of n or with the number of unpaired electron increases, then definitely magnetic moment is also increasing. Species having unpaired electrons are paramagnetic, whereas the species having all paired electrons are diamagnetic. So those species having the unpaired electrons are paramagnetic, whereas the species having all paired electrons are diamagnetic. Magnetic moment is given by the Bohr magnet and Bm, which is given by the expression, right? It is Bohr magnet is nothing but Eh upon 4 pi mc, where H is a Planck's constant, and E is the electronic charge, C is the velocity of light, and M is the mass of the electron. Now, the next property that we are going to study is the catalytic property, right? That is the catalytic property. So, what is the catalytic property of this? So let's understand this thing. What are the various catalytic properties shown by the transition element, right? So most of the transition metals and their compounds have a good catalytic property like platinum, iron, vanadium pentoxide, nickel. So according to the modern theory of catalyst, a catalyst substance is capable of forming an unstable intermediate which readily decompose, yielding the product and regenerating the catalyst. So for example, let's assume if A and B are the reactant, right? So if A and B are the reactant and they will treat it with the catalyst, so it will form the intermediate, that is AB catalysis intermediate, which is unstable. This will readily give the C plus catalysis, right? So the product will be give and you will get the catalyst. Complex formation. So the transition metal are almost unique in their tendency to form coordination complexes, right? So the transition metal are almost unique in their tendency to form coordination complexes. This is due to their very small size. The first one, high positive charge density, vacant or partially filled orbital with the suitable energy to accept lone pair of electrons. So why they form complex, why complex formation is formed in a transition element? So basically the transition metal are almost unique in their tendency to form coordination complex. So they are either unique one. Why? Because due to the very small size, high positive charge density, vacant or partially filled orbital with the suitable energy to accept lone pair of electrons. Right? Now, alloy formation. Since transition elements have almost similar radii, due to this reason, these have a tendency to replace each other from their lattice and form a solid solution over an appreciable composition range. So since the transition element have almost similar radii, due to this reason, they have a tendency to replace each other from their lattice and form the solid solution over an appropriate composition. These are solution are called alloys. So these are hard and a high melting point as compared to the host metal, right? So these are some of the alloys of the copper, like brass. The composition of brass is copper 60 to 80%, and the important properties like they are harder, paler, and more brittle with the more zinc can be added and used in a domestic utensil, condenser, tubes, casting, and they are the use of this. So brass. So brass is made of copper and zinc. So copper 60 to 80% and zinc 20 to 40%. Similar bronze, in which the copper is from 75 to 90% and tin. Similar aluminum bronze having copper value having no aluminum bronze copper 90%, aluminum 90 10% only. That is phosphorus benzene, silica benzene, German silver and the or the nickel silver. This is very important. So in German silver is made up of a three element, that is copper, zinc, and nickel. So copper having percentage 50, nickel having percent, zinc having 30, and nickel having 20%. So German silver or the nickel silver, gunmetal. So gunmetal, what is these three composition are very important. Many time in exam they were asked the composition of these three. right? So basically the German silver having made up of copper, zinc and nickel. So they are made up of copper, zinc and nickel. Okay. Similar gunmetal, copper, tin and zinc. Copper, tin and zinc. And what is the monel metal? Copper, nickel and right. The next is interstitial compound. So what is this interstitial compound? So basically, beta, the transition element also have some tendency to trap small atom like hydrogen, boron, carbon, nitrogen, etc. in the interstitial space. So these transition element also have some tendency to trap small atom like hydrogen, boron, carbon, nitrogen in their interstitial space and thus forming some interstitial or the non-stoichiometric compounds like FeC, Fe10 are the example of the interstitial compound. Like Fe 0.980, Ni 0.980, and TiH 1.7 are the example of both interstitial as well as the non-stoichiometric compound that we know. Now, the principal physical and chemical characteristics of this compound are as follows. That is, the boiling point are higher than that of a pure metal. Right. That is the boiling point is higher than that of the pure. Um, yeah. So the boiling points are higher than those of the pure metal. They are very, very hard. That is some borides. That is a binding compound of boron with the metallic elements approach to a diamond in hardness. Right. They are chemically inert as well, and they return metallic conductivity. So they return their metallic character. Reactivity. So what is reactivity? So the transition element have a small tendency to react due to their high heats of sublimation, high ionization energy, and low heats of hydration. Right? So the transition element have a small tendency to react due to their high heat of sublimation, high ionization energy, and low heat of hydration. They have rather a tendency to remain unreactive or we say noble. Now, nature of oxides. So while moving along the period from scandium to zinc, basic nature of oxide decrease and acidic nature of oxide increase. Behavior differs when oxidation state are different. Simple, if the oxidation state increase, then it will show the acidic oxide, right? So with the increase in the oxidation state of the given transition metal, the covalent character of its compound increase, and thus the acidic character also increases. Like scandium 2O3, titanium O2, V2O5, Cr2O3, MnO2, they know they are the amphoteric. While Fe2O3 and the CO2O3, NiO and CO are the basic one. So let's see which one is basic, which one is the acidic in nature. So the oxidation state of manganese is +2, which is in basic nature. Similar Mn3O4 oxidation amines comes out to be 8 by 3 amphoteric. Similar MnO3 comes out to be weakly acid. Right. So this is how we can actually uh, learn the oxidation state of manganese, that is which of +2 +8 3 3 +4 +6 +7. So we can show that they are so weakly acidic and they show strongly acidic because their oxidation state is very, very high. Similar oxidation state of vanadium and oxidation state of chromium. So remember, mercury can't form any hydroxide because alkali dilute non-oxidizing acid and water or steam have a no effect on mercury. That's why mercury can't form any hydroxide. Remember this one. I hope this is clear to you. Okay. So mercury can't form any hydroxide, right? Because alkali dilute non-oxidizing acid and water or steam have a no efficiency on mercury. Now, before going to F block element, let's discuss some question related to D block element so that you can able to understand the whole chapter, right? Yeah. So basically, the first question is copper from green when exposed to moisture for the long period. So copper become green when exposed to the moisture for a long period. This is due to why? Tell me the reason. This is due to why, beta? The copper, the formation of layer of copper oxide on the surface of copper, the formation of basic copper sulfate layer on the surface of the metal, the formation of a layer of copperic hydroxide, or the formation of layer of basic carbonates of copper on the surface of copper. So this is very much clear. Whenever basically copper, right, whenever copper is treated, become exposed to the moist air. Moist air means nothing but H2O, CO2 plus O2. So this is nothing but the moisture. So when the copper is exposed to the moisture, it will be converted into copper hydroxide, and this is copper carbonate, right? So what's the formation? That is the formation of layer of basic carbonate of copper on the surface of the copper will be formed. Now, second question. Which of the following activate the large number of oxidation states? So this all elements belong to the 3D series. And in 3D series, we know that that is manganese. So manganese show oxidation state up to +7, right? So no one but the manganese, because manganese is nothing but 3D54S2. So, right. So in 3D7 state, it will show zero oxidation state, right? So the maximum oxidation state shown by which of the following element, that is manganese. It will show up to the 7. Very good. Now, the type of isomerism. This question we are going to discuss tomorrow when we study the coordination compound. Till you'll try to solve this question. Iron exhibit +2 and +3 oxidation state. Which of the following statement about iron is correct? So you have to identify the incorrect statement from the following, right? So the ferrous compound are more easily hydrolyzed than the corresponding ferric compound. Ferric oxide is more basically in nature than the ferric oxide. This is true. Ferrous oxide. Ferrous oxide means Fe having +2 oxidation state. And ferric means +3. So as the number of oxidation state increase, acidic character increase. The ferrous oxide is much more basic. Yeah, this is correct. This is the correct statement. Ferrous compound are relatively more ionic. Yes, because we know that as the oxidation state increase, then the covalent. So this will be more ionic as well. Ferrous compound are less volatile than the corresponding ferric. This one is also true. So which one is not true, beta? This, that is first. That is the ferrous compound are more easily hydrolyzed than the corresponding ferric compound. Now the next is the actinoid, lanthanoid, and the actinoid exhibit more number of oxidation state in general than the lanthanoid. This is because. So what is the reason? What is the possible reason behind this, beta? That is the 5 orbital extend further from the nucleus than the 4f orbital, right? So this is basically the reason why this is happening. The lanthanide contraction is responsible for the fact that is the Z and HF about the same radius, right? The Z and HF are about the same radius. So this is the correct option is 3. I hope this is clear to you all. Good. Now, tell me this answer for this question. In a context with the transition element, which of the following element is incorrect? Right. So you have to identify the incorrect statement from the following. That is, in the highest oxidation state, the transition metals show basic character. This is totally incorrect because we know that in the highest oxidation state, they have a covalent character and thus they will show the acidic character, not the basic character, right? So in the lower oxidation state, they show basic character, but in higher oxidation state, they show the acidic character. So this is all about the, this is all from this question. Now move to the next question. That is the element that usually does not show variable oxidation state. So that is, we know that is which of the following will not show variable oxidation state beta? That is scandium. So usually it does not show variable oxidation state. They show only +3 oxidation state, right? Now, the pair that has a similar atomic radius. So which pair having the similar atomic radius? We already discussed when we discussing about the atomic size through a graph. So which of the following has a similar size beta? So that is MO and W, right? Mobilium and tungsten. So this pair has a similar atomic radii. Now, in context of the lanthanoid, which of the following statement is not correct? So you have to identify which of the following statement is not correct. That is, availability of the 4f electrons result in the formation of compound is in +4 for all the members. So this will be not correct. I hope this is clear to you. Good. Now, knowing the chemistry of lanthanoid is denoted by +3 oxidation state, which of the following statement is incorrect? Right. So you have to identify the incorrect statement, right? So which of the following statement is incorrect beta? That is N+3 correspond to generally colorless. So this statement is wrong. N+3 compounds are colored in nature, not colorless. So this is absolutely wrong, right? Now, the atomic number of vanadium, chromium, manganese, and Fe are respectively 23, 24, 25. Which one of these may be expected to have the highest second ionization enthalpy? So already we discussed this thing. So that the second ionization enthalpy is greater for the chromium, right? So chromium having the highest ionization enthalpy. So this is for today. This is all for the today class. That is the transition metals. We already covered transition metal. In tomorrow class, we are going to cover the coordination compound, in which we understand some basic concept behind the coordination chemistry and also try to understand the some J advanced question for this, right? So thank you for the today class, and let's meet on the next class. Till you just revise the whole PPT and just revise the whole concept and try to solve as much question as you can. Yeah. So let's meet in the next class. Take care.